It was fun in yesterday's class. Guys, in this particular class, we will be starting on exoplanets or twin-like planets or Earth-like planets. Am I visible? Hello? Am I visible? Can you guys see me? Okay. Am I visible, guys? Okay, fine. I think now I can see myself. Hi. So we are gonna talk about Earth-like planets and different types of exoplanets, basically. So why are we looking at this thing in detail? We saw in Olympiad that there were questions based on exoplanets. So whatever the current trends are going on in exoplanets, we need to keep updated with it, because they say you have to read the podcast or the lectures that is going on live, so that you can understand these exoplanets in detail, other new astronomical terminologies in detail. And exoplanets is one of those things which comes into play as an extracurricular material that has to be understood in studying for Olympiad examinations. With that away, so when we talk about exoplanets, we know our solar system has planets like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, right? So we have all these planets, and we detected some more planets outside our solar system. So when we talk about outside our solar system, so we talk about exo basically means outside our solar system. We are talking about some extra, or we also use the word extra solar planets. Since we have our own solar planets, our own solar system, we have extra solar systems. Like if you look at the sky, a patch of sky contains billions and billions of stars, and many of those stars has planets orbiting them. So when we look at those particular planets, we call those solar systems as extra solar systems, because we already named ours as solar system. And whenever you look at an exoplanet, there is a nomenclature attached to it, and there is a way we detect it. So all those things we will learn in this particular session. And also we will look at how to calculate Earth-like planets and all those things, which is connected to one of my research work, so which you can get more insight towards. So basically, exoplanets, or the basic definition of exoplanets, are just planets outside our solar system. I think in the current generation, many of you know what exoplanets are. Why do we need to study these exoplanets? So we need to understand, to search life elsewhere. Are we the only form of life that is existing? Are there any life other than our life forms? So many people think we are the only particular life forms that we are here. Hi, oh, now I can see all the chat coming up. Hi, Aishwarya. Hi, Yugant. Hi, Aryan. Hi, Shisha. Hi, Varad. Hi, Nirbhai. Okay, so now now only I saw the chat. I was thinking like I'm talking alone. Okay, good. You guys are here. Sir, I am a part of UCA program. Oh, nice. Congratulations. Hi, Lakshay Yadav. Hi. So we have to search life elsewhere. In order to find life elsewhere, we don't see our life, like human life form need not be the only form of life we are searching. That is intelligent life form I'm talking about. There could be microbial life forms as well. There could be some microbes which can survive in very extreme conditions. If it is too hot or too cold, in such places, also some extremophile life forms can survive. We call those microbes as extremophiles. Extremophiles are microbes which can survive in extreme conditions, and tardigrades are very good examples of those. Tardigrades are these water bear microbes which has 6 legs. It's like a tortoise, tiny tortoise, and you can see through a microscope. Whenever you see a water patch, you can see that. And these microbes can survive in space actually. So that is one of the interesting aspect that we learn from extremophile lives. And what else why do we need to study exoplanets? To understand different atmospheres. There are exoplanets where diamond rines. in that exoplanet, if you have diamonds, you are poor. If you have silica, you're rich. So whatever, it's basic demand and supply problem. And you know who is the diamond scientist of India? Nikku Madhusudan, one of our own Indian student who ended up as a professor. Right now, I think he's one of the readers at Cambridge University. He is called as the diamond scientist of India because he discovered this exoplanet. Sir, what is the criteria for NSEA exam? NSEA exam can be written in different categories. So just go to NSEA websites. Actually, this is just to give you a flavor when you are preparing for competitive exams like JEE and NEET. This is also one of the forms of exams which can help you. And this is like Olympics, right? If you in Olympics, what do? You if you are an athlete, you run fast, you win a gold medal, and you say you brought a gold medal to the country. Similarly, by studying astronomy, and you say I'm the smartest astronomer in this country with respect to this particular program, and say I've won gold medal for the country, and it's a huge task that is ahead of us. So once you clear the national level, you can get into the International Astronomical Olympiad examinations. That's a story for another time. And also find fascinating new worlds. There are worlds where there are 6 star systems. Like there is a planet where we call it as sixulate, or if I don't pronounce it properly, or also you can take a binary star. So if you imagine a binary star, there can be a red star and a blue star. Our star is a yellow star, right? Our sun is a yellow star. There could be a planet where it can have a red and a blue star orbiting each other. So you will have two sunrises, two sunsets, and the color of the sky will be different as well, because the scattering. And why else we need to study exoplanets? To understand the premier question: are we alone in the universe? So we there are different ways people think of. We sent JWST, James Webb Space Telescope, to look for something called as biosignatures, and people are even talking about something called as technosignatures. Okay, technosignatures are these. Are there any technical signatures? Like, are there any kind of a spacecraft, broken spacecraft, or any kind of technology that does not belong to mankind that exists there? So people are searching both technologically as well as biological life forms. So those are the ways we are trying to search right now. You studied in ISRO campus, very nice. And you know, how do we detect these exoplanets? How do we detect them? So the ways we detect them, these are the different ways in which we detect the exoplanets. The first is called as radial velocity or Doppler technique. You would have studied Doppler technique in sound. So similarly, we can study Doppler technique in light. And we can also study a technique called as transit or occultation techniques. And there is a microlensing technique. And the fourth, we call it as direct imaging technique. Let us go one by one and see what they are. So when we talk about radial velocity or Doppler technique, what are we understanding? So very nice to know that many of you from UVK are attending here. So when we talk about Doppler technique, let us imagine this is me being an astrophysicist. Let me put myself here, or let me put my daughter here. Okay, let us think she becomes an astrophysicist in the future, if she wants to, if her heart says so, falling into the limits of Three Idiots. Okay, a joker, oh man kahega, right? Whatever. Okay, we'll not go there. So when we talk about a star, let us imagine, just like sun, there is a host star. We call that as a host star. Host star. There is one star which is hosting, and let us say these are the planets. This is one planet which is orbiting this particular host star. So when you are observing this particular star and take a spectra of it, you take a spectroscopic spectrograph of it. So what happens is, when the planet is going away from you, the lines in the visible spectrum or optical spectroscopy, it tends to shift towards the red side of the wavelength. So you know, in optical spectra we have VIB-GIR, right? We have VIB-GIR. So you see, whenever the star is going away, okay, when we say spectrograph, it is basically spectroscopy. Okay, what is basically we are talking of spectrum. We take light source and we put gratings to it using telescopes, and we generate a spectrograph. This is what I did in my discovery of new stars. I told I discovered two or three new B type emission line stars in my PhD work. So when we did this, what we actually did was we looked for H alpha emission line, okay, 6563 angstrom, whether it is in emission or absorption. So you will be learning all these things because this is very much needed in analyzing the spectroscopy related question in the NSEA program. Okay, so spectrograph is basically an instrument. Okay, spectrograph is basically an instrument like you know what is diffraction grating, Hardik is asking what is spectrograph. So do you know what is a diffraction grating? Or imagine if you put a prism, when a light is passed, you see 7 colors. That is the spectra, right? Similarly, in a telescope, put a diffraction grating. Put a diffraction grating to the star. So whenever the light passes through the diffraction grating, you will see the spectra of it. So we put slits of different wavelength. For example, we have something called as GRISM 7, GRISM 8. So we will not go to those grades. That is way too higher. Imagine just a diffraction grating. Okay, so the light gets scattered and you see dispersion lines, and also you see you can get, if you put a slit to it, you can get a spectrograph of it. So once you get the spectrum, so whenever the planet is going away from you, the lines gets shifted towards the redshift. Okay, we call that as redshift when the planet is going away from the observer. You are the observer here. Let us say Hardik is sitting here looking at this planet. So whenever the planet is going away, in his spectrograph, he will see the lines have been shifted towards the redder region of the VIBGYR, this side. Okay, and when the planet is coming towards you, in the spectrograph, you see the lines getting shifted towards the bluer region. So this is basically due to the wobbling of this particular star, because the planets are orbiting, the star is wobbling because of the gravitational pull, push and pull. So because of that, star wobbles, and this particular shift, red shift, and this particular blue shift, we call it as Doppler shift. Okay, this we call it as Doppler shift technique. This is one of the way we say there is a planet which is orbiting a particular star. This is one way of detecting an exoplanet. Is it clear? Any doubts? You guys can ask me. There is question, there will be equations. They will ask you to find the Doppler shift, which will be given in detail if you join the the program in the Vedantu platform for NSEA. I think I'll be teaching these things when we talk about how do we calculate the wavelength, how do we calculate the Doppler shift, all these things in detail, because there are questions related to Doppler shift. Sir, can you show I can show you a spectrograph. If you are in one of our programs, I think I can show my own work. Right now, since this is not there on the PPT, I can just show you, like I can write and show you how the spectrograph looks like. You know, it will look like this, something like this. It will look like this. So it will be wavelength, or basically shifting. Okay, here you will write a certain wavelength, say 6563 angstrom, which is H alpha, so on and so forth. 4000 to 7000 is the visible wavelength spectra. So when it shifts towards the 7000, we know it is red shifted. When it comes in the other region, we say blue shifted. So that's how the spectrograph looks like. You see emission and absorption lines. Yeah, I'm an astrophysicist. So Yash, you can Google my name. You will know full. You can type my name in Google or Amazon. You will find all my details. You can just type Madhu Kashyap Jagadish. You will get all the details about me. Okay, so I have made it simple. So second way of detecting exoplanet is through transit and occultation. What do you mean by the word transit? Transit is basically eclipsing. Okay, transit is basically eclipsing. Let us imagine this is a big star, and there is a planet which is orbiting this particular star. So when there is no planet, or when there is no planets disturbing this, when you plot brightness on y-axis, time on x-axis, you will see a linear graph because the brightness will be constant. But whenever the planet passes through this particular star, so the brightness will dip. There will be a dip in the brightness, and again after the planet passes off, the brightness becomes constant. So based on this particular dip, you will be able to find a exoplanet, and looking at this depth we can find what is the radius, mass of the planet as well. Okay, and what do you mean by occultation? Occultation is when the star is in the front and the planet is at the back. This is transit technique. What I am showing this as an example is transit technique. This particular technique is called as transit. So when this star is in front and the planet is in the front, like for example you are watching it here, let us say my eyes is the observer and this my hand is a star, and if the planet is my pen, okay, you can't see that, I think I went away from the screen. Let me come back. Okay, so here it is. So my eyes is this, so my hand is star, the pen is the planet. So this particular region, this particular alignment, we call it as occultation technique. When the planet is behind the star, we call that as occultation technique. Sir, but both star and planet look like a speck of dust. How we know it's a... That's why I'm telling you, you plot a graph. You won't be able to... This is just a artistic impression I'm showing you. The majority of the work is done by this graph. You know, the graph will show you this particular dip, so you can say it is transiting. After that, for verification, you can measure the occultation. Okay, you can measure the occultation for verification purpose, but initially we use transit technique to detect the exoplanet in the first place, Hardik. Okay, one more way of detecting the exoplanet is through microlensing technique. So we call it as particularly gravitational microlensing technique. So you are an observer here, okay, and there is a source star here, and let us put a lens, okay, star lens we say. The planet is here and we put a lens of a star, and this is basically through Einstein's general theory of relativity, or also called as Eddington's bending of light. Okay, so imagine the entire space-time is basically a big rubber sheet, and you put a heavy mass, so the space-time bends. So if there is an object like a star behind that particular star, the light tends to bend through this curve. Because of the mass, the mass of the star, the space-time would have created a curvature. So Einstein called this as curvature as gravity. So the definition of gravity varies once you go for higher education. It keeps on varying, and this is one of the techniques in which we detect the exoplanets. And direct imaging is one of the imaging we actually use for exoplanets. So you will see for when you took the image few years back, how far away the planet has moved. So based on that orbital disturbance of that particular star, you will be able to detect the planet. And you know, Nobel Prize was given to these people, the authors of this particular paper, Michael et al. There was a star called 51 Pegasi. This is the first exoplanet that was detected. This is the very first exoplanet that was detected, and this work was published in 1995, guys. This work was published in 1995, not so late, not many years ago, after 5 years of my birth. So that's very small number. So 51 Pegasi is the host star, and when we say A, B, C, D, the nomenclature works this way. So when we look at A, B, C, D, A will be the first orbit, B will be the second orbit, C will be the third orbit. Just like a Mercury will be in the A orbit, for example, if you take as our solar system, our sun will be called as 51 Pegasi, Mercury will be called as 51 Pegasi A, and Venus will be called as 51 Pegasi B, like that. I'm just telling you as an example how the orbits work. So this is basically the orbital number of the planet, okay. So it says you can know this is in the second orbit. Hello Zero. And Alexander Vonkov was the one who discovered the first exoplanet in the constellation of Pegasus, and but the actual astronomical breakthrough, even though he detected that, but first measurement and first existence scientific proof came by Michael et al. 1995. And once they discovered it, people wanted to study that. So space mission started. CaRoT mission in 2006 was the first mission by French European Space Agency which started this. Then it was followed by the very famous Kepler Space Telescope in 2009 by NASA. And now recently we have James Webb Space Telescope, which is studying our exoplanets. So does our Chandrayaan-3 instrument that is located on the dark side of the moon. Okay, and this is one of the way we detect twin Earth. So we call this as Earth Similarity Index, or ESI in short. So how do we define ESI is, let me write it in the way you guys will feel it as easy. So if the ESI value is equal to 0, that means it is 0% similar to Earth. Okay, if it is 1, it is 100% similar to Earth, and if it is 0.8, that means it is 80% similar to Earth. That's how we compare Earth with other planets to check whether they are similar or not. So in order to find the twin Earth, we keep a threshold to be 80% and above. Now these parameters, this R is what all we look at for finding twin Earth is radius, density, escape velocity, and surface temperature. So these are the 4 parameters we work or take the geometrical mean of to find the similarity of exoplanets. Okay, and what we are doing is, let us say this is X is some exoplanet. This naught is basically the reference value for Earth, whatever the reference radius of Earth if you are taking. So whatever the radius of exoplanet minus the radius of Earth. Similarly you do this, and m for our calculation purpose we can put it as 1. Okay, and weight exponent will be based on the parameters that will be given in your examination questions. Like for example, the weight exponents of particular for Earth, it can be measured and given to you in the question as an input. Okay, then you will say this is this much, the size of the exoplanet is similar to Earth. Then you do the same thing for density and escape velocity and surface temperature. So when you take the geometrical mean of all the 4, radius, density, escape velocity, surface temperature, you can write like this, or the radius and density we call that as interior parameter of ESI, interior parts like radius and density, whereas the surface part, S stands for surface, I stands for interior, S stands for surface. And when we take the geometrical mean of both, we call that as global ESI, means the total ESI. Okay, what is m? M is basically an order, input variable order. We set it for 1. Okay, it is just an order at which the value is being compared towards thus. Okay, so that's how we do that. And so when we take the geometrical mean of all these 4 parameters, we get answers between 0 to 1. And Mars will come around 0.8. So we keep Mars is little similar to Earth. Okay, and I keep on telling all the people, instead of polluting Earth, go and pollute Mars because Mars has very thin atmosphere. So if you can make a very thicker atmosphere, then the rain might start coming onto the ground, and good things will start happening on Mars. And there are many issues, like magnetic field is also an issue, because we need protection from high energy cosmic radiations that is coming out from the space. So Earth has a magnetic field which will deflect these cosmic radiations and high energy solar radiations away to protect us from cancer. But Mars does not have a very good magnetic field. So that's why astronauts are asked to wear magnetic suits to work on Mars especially. Will Vedantu be providing lectures on YouTube? Actually, there is a course which is being run right now. So you can look at the link in the description and you can join accordingly. I know that is what is happening right now. On YouTube, I think there are few sessions that will be run on YouTube as well. Okay. Sir, how can I connect to you personally with? I don't know. Okay. Yeah. So actually when we did this work, actually I was a part of this work. And this is my own paper. You can see here, J.M. Kashyap et al. 2017, Astrophysics and Space Science Journal. This was published by me and my team. I had a Russian scientist who was my co-guide along with my supervisors. We published this in 2017, and this became the cover page of Astrophysics and Space Science Journal. And this was the formula. Many people ask me what was the formula you discovered. This is the formula which we discovered, and we had negated Venus because Venus has a temperature much higher than Mercury. Even Mercury is much closer to the sun. Venus has much higher temperature than Mercury because of atmosphere. It interlocks the atmosphere, so the heat gets trapped, just like the greenhouse effect gases gets trapped in Venus. So the temperature gets so hot it will go more than 700 Kelvin or so. So that's very hot. And when we talk about Earth's surface temperature, it is around basically we talk about 288 Kelvin. Sir, please describe your formula. This formula was to find, we used to find something called as equilibrium temperature. Okay, equilibrium temperature. But finding surface temperature is challenging. The reason is there is a parameter called as albedo. I'll be teaching about albedo in the course in detail. Albedo is basically the reflectivity parameter. So mirror has very high albedo. We can say reflectivity, very high reflectivity. So albedo is basically related to reflectivity, and Earth has 0.3, around 0.3 albedo. So keeping albedo parameter we can't calculate for because it's based on atmosphere. We can't go to exoplanetary atmosphere and check for how reflective these particular planets are, right? So for that we had to skip the part of albedo, or fix albedo to be similar to that of Earth, and then create a linear regression and find a relationship between equilibrium temperature and surface temperature. So what we did was we took the planets in the solar system and we took all the exoplanets and we fitted with the linear regression, and when we wrote a program, these numbers came out as constants, and once we matched it with the exoplanets, they are very close to this. And because you might be wondering, this number is little higher, that is because of the correlation changes of the planets. This is not there in the syllabus, this is just an extra information I'm giving you. And when we did this, we found around 9 Earth-like planets, if I'm not wrong. We found in our work, we found 9 Earth-like planets, 9 planets which are twins of Earth's. Okay, 9 planets which are similar to that of Earth. So you can see here Mars has, sorry, not 0.8, 0.73 to be exact. So Earth is 100% similar to Earth, obviously. Mars is 73% similar to Earth. There are these planets, Kepler 438b, GJ667cc. I'm talking about 2017 data. Now the data will be different. This is 2017 wala data when I worked. And this is Kepler 296e, and this is Kepler 442b. And you can see that this is 91% similar to Earth, this is 90% similar to Earth, and this is 0.89%, this is 89% similar to Earth. We kept Mars as the level above which we can call them as potentially habitable planets. So when we talk about habitability, if you have a star, if the planet is too close to the star, it is too hot. But if the planet is too far away from the star, it is too cold. But for Earth-like planet, the temperature is just right to sustain water and host life, right? So the distance matters a lot. And many people ask me, sir, moon is also in that place, does moon has life? So there is something more missing in the research of the definition of habitability or Goldilocks zone. I keep telling this. Moon, because this is an argument, this is a work which is going as research still, so on and so forth. Even I am working on it, and many people are working on this particular problem of defining habitability in much precise way as possible, so that we can compare them. Hi Babu. Hi Roshan. Okay, so that's how we found Earth-like planets. In our work, we found 9 Earth-like planets and 12. We also found Mars Similarity Index, but time has run out, so I won't be talking about twin Marses. So we found many 12 Mars-like twins in our work, 12 Mars-like planets. So that is a story for some other time. Guys, this is a program for Astronomy Olympiad. If you have not registered, I highly appreciate. I would really encourage you to go and register, and we can have fun. This will be a course of 24 sessions. So the already just an introductory class has been completed yesterday, and you have not missed much. You can always watch the recording. If you join the program now, I think you will be able to cover the entire Olympiad syllabus with me, and we will be solving a lot of problems. You'll be doing a lot of assignments, tests. I think if you can bring a gold medal to our country, that will be the dream. And I have students previously. I have taught students in previous places where I my own students have cleared NSEA Olympiad. So until sir, where is Kepler 438b? Kepler 438 system, it's called as Kepler 438 is the solar system, and B is the second exoplanet that is orbiting the star Kepler 438. Okay, Kepler is a space telescope. All the planets and stars, we will be talking about those coordinate systems when we talk about right ascension, declination in the upcoming sessions. Okay, so until then, it was really nice and wonderful knowing you all. So if you have not joined, you can look at the link in the description, and you can always ask go to the Vedantu app and get along. uh, इतना smart, I don't know यार. I don't know Akshat. Okay, sir, can one orbit have two planets? Oh, that's a nice question to think about. You're talking about binary planet. Can it be possible? And that's a nice question to think about. I think we should think about that. I think it's difficult to it may collide, right? There is a chance of the gravitational force will be so bad, there will be a difference in the orbit. No, even though binary stars orbit around each other, their orbital planes are different. So if such a planet exists, how do we detect them, yeah? That's a very good question. That's a very good question. With that question and thought, we will look into that. Maybe the research group will look into that, and maybe my I need to think about it as well. That's a very nice question. Very nice. Okay, guys. With this, we will close this session, and I would like to see you guys in the class. Until then, have a nice day. Take care, and bye bye.